Control Systems, Chapter 3, Lecture 2. In this lecture, we'll look at, if we're given a transfer function, how to go to the state space representation. So one of the key advantages of the state space representation is its ability to model and simulate physical systems on a computer, for example, using software like MATLAB. Many real-world systems are initially represented using transfer functions, and this goes back to the way it was historically done. And honestly, sometimes it's easier to come up with a transfer function. If you're given a differential equation, just take a Laplace transform, and you can quickly come up with a transfer function. However, to leverage state space analysis for simulation and control design, if we have that transfer function, we want to convert it to state space form so we can get it into MATLAB. So let's see how to do this. Let's consider this following transfer function that we're given. And so here's our representation. So here, the first thing we want to do, step one, is to find the associated differential equation. So our transfer function is represented by here. Here's our output. Here's our input. This is our transfer function. So we can sort of cross multiply, and then we can take the inverse Laplace transform of the following equation. So we have s squared times y, that's going to be y double dot, plus 3s times y, that's 3y dot, plus 4 times big Y, take the Laplace transform, this is 4 times y, equals small r. So here we're also going to assume that all the initial conditions are 0. So y sub 0 equals 0 times 0, y dot times 0 equals 0. So here's our differential equation represented here. So now we can, we want to select our state variables, and typically we'll let you use x1 and x2 to represent our state variables. So let's let x1 be y and x2 be y dot. So you take x1 dot, that's y dot equals x2, flip that around and you get x2 equals y dot. So let's write these as two first order differential equations. So here we have a second order differential equation, and we're going to transform it into two first order differential equations. So here we want, here's our state variables x1 and x2. The left hand side is always going to be x1 dot and x2 dot. So x1 dot is simply y dot, that's x2. x2 dot we get by taking this term and this term and shifting over to the other side. That's y double dot, which is x2 dot. It's minus 4x1 minus 3x2 plus r. This set of two first order equations we can write as a single matrix equation. So we have this matrix equals, here's a 2 by 2 matrix times x1, x2 plus a 2 row, 1 column matrix times r. And the output is simply going to be written as a matrix times a matrix again. So you multiply this out, what do you get? You get y, which equals x1, is simply going to equal, if you multiply this out, it's going to be x1, right? 1 times x1 plus 0 times x2, it's simply x1, so y equals x1, which we know from up here. So in summary, we were able to take a second order differential equation and transform it into two first order differential equations. Here, we put it in the standard form. X dot equals ax plus br, y equals cx plus du. Here you can simply look at it and you can pick out what the A matrix is. The A matrix is here, 0, 1, minus 4, 3. The B matrix is 0, 1. The C matrix is here, 1, 0. And the D matrix is simply 0. So in representing this system, oftentimes people will they'll just write down what the matrices are. So they'll list A, B, C, and D. That's your state space representation. So let's try this for another example that's a little bit more complicated. Here we have a S in the numerator. So here's our new input and output with our transfer function. But we're going to take this transfer function, we're going to break it into two blocks. So we have a block with the denominator and a block with the numerator. This first block we solved already. This is essentially the solution to the first example. So let's look at how to solve this. So you got an input, you got a transfer function, and you got an output. So for the second block, again, we're going to write this as y sub s equals 5s plus 2 times x1. So taking the Laplace transform and noting that x1 dot equals x2, we can write this as 5 times, so you got s times x1, that's going to be 5x1 dot plus 2 times x1 equals, so here, we want to order this such that x1 appears first, so it's 2 times x1 plus 5 times x2 equals, we can write this as a matrix, 2, 5 times the column matrix x1, x2. So now we have the whole thing because we solved the first set of systems in the first example, and we found the output equation was given by the following. In the second example, we found what y is. So here's our solution. And again, if you want to represent this in the state space form, you can simply list what A, B, C, and D are. So in our example here, if we want to represent, here's our standard form, we would just list the matrix A, B, C, and D in that order. So once we have this transfer function, we can plug it into MATLAB, and MATLAB will convert it to state space form for us. Here we enter the numerator, we enter the denominator, and we use the space transfer function, the state space function as part of the control systems toolbox, and we display the result. Now, one thing to note about transfer function is that they are not unique. There are different ways to do it, and the MATLAB control toolbox uses one method, and that's different from what our textbook uses. But so in order to convert the form that you get out from MATLAB into the form that our book uses, we're going to use the following conversions. We're simply multiplied by a identity matrix, and when you do that, you get out exactly what A, B, C, and D are, exactly like our textbook gives us.